I do think that the unexplainability issue is actually a little bit overblown in the sense that I don't think you can explain human behavior either. And so this is, the only alternative that we have over an AI decision maker is a human decision maker. And you cannot explain how the human decision maker works. So I wouldn't disqualify the AI based on its unexplainability, because the alternative is equally unexplainable.
Welcome to XgridTalks. Today we are going to talk about reinforcement learning, introduction, algorithms and uses. With me is Mr. Kastner. He is an ML engineer by profession. He is the founder of Collectivize and a venture partner at Post-Urban. And his area of specialization include human-centric augmented intelligence, ethics in AI, and AI in society, edge AI, distributed learning, near real-time data pipelines, and collective intelligence. He is a renowned TEDx speaker, and he has talked on many global platforms on AI and related topics. His own initiative, Collectivize, provides services rooted in collective intelligence and human-centric design so that organization can make better decisions to achieve their goals. So Johannes, welcome to the show. Really nice to have you here.
Thank you very much. Thank you for having me.
Okay, that's great. So let's just get to it. Okay, so how is it possible for AI to make those complex decisions in unpredictable environments?
Nothing is harder to predict than the mind of an opponent in some game. And that is by design. The opponent's strategy includes creating unpredictable. As an aside, this is in no way restricted to the innocuous kind of games like chess or Go. Remember that game theory was constructed to devise strategies in the Cold War. The decision that is to be taken in a game is a contingency strategy. That is to say, one has to decide on a plan, maybe a probabilistic one, at least several steps ahead, in an environment that is highly unpredictable. In addition, if the algorithm you are to create is to play the best Go player in the world, say, as that was the goal and the result of the AlphaGo system, you can't rely on data from human play. When the goal is to outperform the best human player alive, you obviously can't accomplish this goal by mimicking human behavior, as that has a performance ceiling, which is lower than the performance of the best player. For that, you need some other way of learning. The other way that has been used to incredible effect is called reinforcement learning. And it comes out of a behavioral theory about the way in which animals or living organisms are learning. Pioneers of this theory and the associated experimental evidence about animal behavior are Pavlov, Watson, and Skinner. This body of work is called behaviorism, and it began in the late 19th century with Pavlov. This work is descriptive, as it was meant to describe animal behavior. Here, it becomes prescriptive for our algorithms. That is to say, our algorithms are built to maximize reward and minimize costs as they take experimental actions in their environment. Does that make sense so far?
Yeah, definitely.
They do this as animals might do this in their environments, trial and error. In order to get superior performance to humans, they must either do this smarter than humans do, or they must spend more time experimenting. Of course, they can experiment in parallel, as that same algorithm can play thousands of games at the same time on their own. They can play against themselves and improve themselves in this way, right? While the best human player surely plays against himself and studies strategies from the past, the human player cannot do this in parallel thousands of times, as she has finite time. This alone can make the difference right there. It puts algorithms over the top.
So let's just maybe describe reinforcement learning to a layman. Like, go to the basics here.
Absolutely. Well, the first thing there I would note is the word reinforcement itself. It holds most of the definition. Reinforcement learning is about teaching a machine how to take helpful actions by reinforcing them with rewards, and to avoid harmful ones by reinforcing them with a cost. A cost is actually the inverse of reward, so they're really the same thing. So they can be interchanged. Right? So minimizing cost is the same as maximizing reward. A cost is a negative reward, and a reward is a negative cost. We thus teach a machine the same way that we teach a dog a trick, sticks and carrots, if you will, except that both rewards and costs are given in terms of numbers, and that long-term value of taking certain actions is considered, and not just the short-term reward. Also, future expected rewards are discounted for the reason that they are less certain to be reaped, and also the passing of time has a cost of its own. If you play chess against an opponent, for example, your reward for playing well is to win. You receive a positive number of points. And this is mimicked for the machine by rewarding its policy in a similar way in which human play would be rewarded. Note that an action can never be taken with perfect predictability, as this would make it easy for the opponent to learn your strategy. Instead of predictable actions, then, what is learned is a policy, which is to say a few beneficial actions in each contingency, together with the probabilities, to enact them in such a way that they're optimal. If you have taken a game theory course or a course on optimal control theory, this should all be familiar. Else, I'm afraid this will sound a bit foreign. In the case that these last ideas are foreign, just think that we're optimizing a whole strategy of potential actions and potential probabilities of taking them, those actions, that also include an optimal level of surprise for the opponent.
Great. So reinforcement learning is a subset of machine learning, neural nets. How do you define it?
Yeah, so that helps to first explain what supervised learning is, and then I'll talk about reinforcement learning as a modification of supervised learning, because that's really what it is.
Okay.
You can think of it as semi-supervised learning, in fact. There's also an area in machine learning called unsupervised learning, which isn't relevant here at all. So I just wanted to mention it for completeness, as these are roughly the three types of learning that are listed in most textbooks on machine learning. Again, these are unsupervised, supervised, and supervised learning, and semi-supervised or reinforcement learning. Sorry. AI, to remind our audience, is the field of study and practice relevant to any machine behavior that is intelligent, including learning, but not exclusive to it. So AI is a study and practice around a set of smart or intelligent behavior ascribable to machines, of which machine learning is just a subset. What other things you might ask before belong to AI other than learning? Because this is not often discussed. For example, there are things like deducing something by means of logic. I don't know if you've seen theorem provers. There's sort of algorithms that can solve a mathematical theorem, for example. And this logical ability, this may be learned or it may not be learned. So there might not be any machine learning involved in this at all. But if you can solve a mathematical theorem, there is something intelligent about it. And in fact, Noam Chomsky has famously argued that some of our own intelligence, our own human intelligence that is relevant to language, must be hard-coded before we can even start learning language. So there might be some things about intelligence that is not learned at all, it's just hard-coded. So here, I only talk about machine learning. So we're restricting ourselves here, because reinforcement learning is part of machine learning. And so we're talking about reinforcement learning, and that is one of three types of machine learning. Reinforcement learning doesn't include in its definition how it is implemented exactly. So it could be done with neural networks or other ways. The only thing that is required for reinforcement learning is that there is an agent in some environment which learns from a reward and cost mechanism, roughly based on behaviorism. The environment can be minimal, it can be rather complex. It learns a policy by trial and error, but how exactly learning is implemented is not prescribed in its definition. Neural networks are one way to implement reinforcement learning. In fact, probably the most common way now. As they originally were built for supervised learning algorithms, and they can be ported into this new form of learning, let's begin to talk about neural networks after I introduce supervised learning. I have to begin with a bit of terminology. Supervised learning is used to learn a label from a set of features. A label can be a string denoting one of many classes that an object belongs to, such as the word cat or the word monkey, And the corresponding features would be the data that is used to distinguish between the classes. So for example, the features might be the ordered pixels in a picture of a cat, and the corresponding label is the word cat. A label could also be a continuous quantity that is to be predicted, such as the unemployment rate next month. And there, the features would be the various variables that can be used for the prediction, such as the current and last period interest rate and the price of labor, etc. The supervised learning test then, in the first case, for the algorithm to learn how to take in ordered pixels in a picture and output corresponding labels that describe what's in the picture, such as bird, monkey, or horse, or person. In the second case, it is to learn how to take in current and past facts, such as the interest rate, the wages of various professionals, and to predict the future employment rate, for example. This is done in general by fitting some model from the combination of features and labels in a small data set known as training set. In other words, the model knows the right answers for all of the elements in this data set, and it learns to figure out how the features can be used to predict the known labels. The trained model is then tested on another set of examples for which we also know the right answers, known as the test set. We withhold the answers from the model and ask it to tell us its predictions. We can then compare the model's predictions with the correct answers that we know. There are many variations of this approach. One way to solve these problems is to use one or the other neural network as a model. Or we could use some other rather completely different algorithm, such as boosted trees, which sometimes outperform neural networks in practice on such tests as the second one, the prediction test of a quantity from other quantities. Neural networks, especially convolutional neural networks, do really well on vision tests, but others, for example, recurrent neural networks, do better on sequence prediction. Autoregression and also natural language prediction, translation, summarization test, also done with recurrent neural nets of some sort. As an aside, the newest and most powerful such sequence prediction neural networks is called the transformer, which has some major advantages over previous approaches. Since it's not the goal here to talk in detail about neural networks and how they work, I will have to leave that to another session. Here I want to next demonstrate to you how supervised learning is insufficient for some task and why we need something beyond that. I've already alluded to that earlier when I talked about the chess game. If you teach an algorithm, remember, to predict your own behavior in a chess game, then the algorithm can asymptotically learn how to play like you. But you can do this in a supervised way where the label is every next move you take, given all the past nodes. And the features are all the past actions and the constellation, in fact, that you're in at the moment in the chess game. And however, if you're solving this problem of getting an algorithm to outperform a human on some task, for example, playing chess or Go, it wouldn't be sufficient to learn from the behavior of a human player, even the best player, as learning to imitate a player would preclude the algorithm from ever outperforming the player. Imitation isn't, if you think about it, imitation is actually not that intelligent in a way. I think that this is an intuitive thing that's made a little bit more, that it's made more concrete here in this case. So then reinforcement learning comes in where the algorithm learns from a reward mechanism. That is to say, it learns how to beat you by predicting the moves that would surprise you and that would lead you to lose. Where your loss and the algorithm's win is the new label, if you will, that is to be predicted from the features which include the algorithm's potentially novel behavior as well as opponents' reactions. Previous approaches work well when the target or the label that is to be predicted is static. Reinforcement learning comes in when the target is a moving one. Interestingly, you can use the same types of algorithms that were used for supervised learning in order to learn a static label, to learn this moving target. So yes, therefore you can use neural networks as part of your solution. You could also use some completely different approaches, such as gradient boosted trees, as I said before. The important difference to remember between reinforcement learning and supervised learning is that you learn to predict rewards from your own actions in some environment instead of just static labels in a supervised learning environment.
Okay, that's great. So is it true like this reinforcement learning looks at a problem as a whole, which might not be the case for ML?
How the algorithm is rewarded and what you mean by a whole, that's really important here. The short but probably not satisfying answer to that question is that if the rewards and costs are based on the whole, then it will actually consider the whole. That is to say, if you're rewarding the algorithm to consider everything relevant to you in terms of the outputs of the system, then it would also consider everything relevant to you in learning and making its decisions. So all the features will also be considered, in sort of getting all of the outputs, right? You have to consider all of the features in the structure. Of course, rewards are a useful metaphor, and it's impossible to literally reward a machine. The machine is in reality just optimizing a function, but it is very helpful to think of it in terms of rewards. So concretely, Facebook's feed algorithm, for example, may or may not be a reinforcement agent, but let's pretend for the purposes of this discussion that it is, and that it is rewarded entirely based on human attention that is paid to its items in the feed. If these two conditions are met, then it would likely favor posts that are racist or otherwise bigoted. Why is that? Because they garner attention. So if someone says something outrageous, we will all be forced to pay attention to it. So then, to get back to your question, this algorithm would be a reinforcement learner which considers the whole, if by whole you mean everything relevant to attention, and it fails to consider the whole if you mean something different with this expression, such as the well-being of users, decency, etc. You would have to include those other things into the reward mechanism in a quantifiable way. And then those other considerations would also be considered by the algorithm. You see, in fact, the reward mechanism should specify exactly how the various considerations are to be traded off against each other and how they're complementing each other. So in economics, we call this specification a utility function. And in some numerical function, it is some numerical function that maps any configuration of valuable factors you value to one number that represents the reward you get from this particular configuration. So if you reward the algorithm with everything you value in the utility function, which correctly expresses how you are willing to trade off factors and how they complement each other, then it will mimic your values and it will learn how to serve them, most likely better and more faithfully than a human could. The art then is to express your values in the form of a reward function or a reward mechanism. And this actually is not trivial at all. What is special about reinforcement learning is that the target or the label is a moving entity, and that we are in a highly dynamic environment relative to other machine learning tasks that can only handle a static world. Of course, not all reinforcement learners are built equally either. In order to get such superhuman performance as an AlphaGo, you need very powerful algorithms as well. So it's not just the reward mechanism, but the reward mechanism is probably the trickiest thing. But you also need great neural networks or whatever the top algorithms are that currently do the best. However, I think that the most important thing is still to pay attention to the reward mechanism. If you get this one right, your algorithm is at least trying to solve the correct problem. And if you're not, then the best algorithm won't do any good at all. In fact, the better the algorithm is, the better it solves the wrong problem, which could be actually worse than having a not so good algorithm solving the wrong problem. So only hunt for the best algorithm, that's my advice, once you are sure that your reward is right. For the best algorithm, there are a lot of things you can try, and I would recommend just doing that, just trial and error. The same way as a reinforcement learner itself will do it then afterwards. It always depends on the use case. So start simple and establish a benchmark, and then only after that add complexity, and only if it is warranted in the sense that it significantly outperforms the benchmark model.
Which industries are already using reinforcement learning at this moment?
Well, it all started, as far as I understand it, with the elevator scheduling problem, which you might have heard about. This is a surprisingly difficult problem. So the problem with scheduling elevator cars is known to be NP hard. NP hard means basically it's not solvable by traditional methods, and it's hard, really difficult to solve. And this means that no optimal solution is actually known, right? That's what it actually is defined as. And therefore, you need an approach where the system learns a strategy, because that, to fit a near optimal model, even if you can't get an optimal model. And then, from that you can see, stabilizing a drone in a highly turbulent environment is a good use case, and then that is certainly where it's certainly used for. And then robotic manufacturing and robotic supply chains is, most obvious use case, I think. And then one example of how reinforcement learning already has made a big difference is in the use of AI agents by DeepMind to cool Google Cloud data centers. This led to a 40% reduction in energy spending. A lot of money is being pumped into self-driving cars. So this area has multiple up and coming use cases. And we've all been waiting for this to find major acceptance and everyday prevalence. AWS Deep Racer is an autonomous racing car that has been designed to test out reinforcement learning on a physical task. It uses cameras to visualize the runway and the reinforcement learning model to control the throttle and direction. Of course, in finance, this form of learning is highly relevant, as we have a very dynamic system and a large action space. IBM has built a sophisticated reinforcement learning-based platform that has the ability to make financial trades. It computes the reward function based on a loss or profit that is based on the profit for every transaction, for every financial transaction. The most life-saving applications, though, of reinforcement learning are likely in medicine and patient care, especially in volatile settings. So applications include dynamic treatment regimes, chronic diseases, or critical care, automatic medical diagnosis, for example. The use of reinforcement learning in healthcare can enable improvement of long-term outcomes by factoring in delayed effects of treatments that might otherwise be hard to correctly consider. Assisting in innovation and patent creation is a more speculative but potentially lucrative use case. But we can't say that currently people rely on reinforcement for this. Other currently explored use cases are predicting risks from unfolding hurricanes and assisting in rescue missions in near real time. Obviously, there are military applications as well. Importantly, but still largely in the future, reinforcement learning could assist governments in innovating in the policy space and managing volatile situations of all sorts to prepare for the near and far future in terms of energy, food, water, transportation, and really all sorts of sectors in which events and considerations are not static and are not so easy to predict.
For an AI-based startup, what elements would be essential to provide services related to reinforcement learning?
Great question. First, you want to be sure that you're using reinforcement learning for the right reasons. There are other options as well that might fit similar use cases, and you might want to study them as well. For example, genetic algorithms. These are algorithms that are, instead of being based on animal behavior and how animals learn, they are based on evolution. That's also an interesting class that you might want to explore. You need to define the agent, that is the internal policy and the learning algorithm to improve it. So the environment is everything that is relevant to our problem and that's outside of the agent itself. This environment could be a robotic body of our agent, as well as the physical environment in which it acts, or a simulation thereof. Or it could be a virtual environment, such as an electronic trading system or crypto currencies, together with the whole internet as a source of information, for example. It really depends on what you are building and what sort of use cases you have in mind. The environment really includes everything, including the body of the robot, as I said before, that is outside of the agent. And the agent is just defined by the learning algorithm, and the policy. The agent sends its actions that it takes into the environment, and the environment generates observations and rewards for the agent. If the agent doesn't have any prior knowledge of its environment and starts learning directly from it without having a model of, say, such things as, say, Newtonian mechanics, for example, to understand the impact of gravity, then the learning, then we call it model-free learning. The agent is dropped into its environment and learns everything from scratch in this case. Of course, if we give the agent models where we have them, which seems a smart thing to do, we speed up the learning substantially with model-based reinforcement learning. In those cases, the agent then can learn from all previous human experience and theorizing, as well as from its environment. Simulating the environment rather than using an environment in real time directly for training has some added benefits of, like, for example, one, being able to learn in parallel, as one can simultaneously train in thousands of simulated parallel worlds. And two, it can create counterfactual worlds in which things have already occurred that we are trying to prevent, that we don't want to occur in reality, or that are implausible but still possible, but yet never happened thus far. Right? This is sometimes important to learn what to do in situations we've never encountered before. Right? If you want your agent to be robust to circumstances, this is a great idea. Next, the reward function. In economics, known as the utility function. I talked about it before. This is probably the most critical thing to get right. It expresses the value, the ethical values, as well as the business priorities of the people on whose behalf the agent is to act. Let me rephrase this. This is really important. The rewards that the agent earns and how it earns these must represent the values of the stakeholders on whose behalf the agent acts. The rewards can be sparse. For example, if you reward an agent only once the chess game ends, with either negative or positive rewards, then this is a sparse reward, as it doesn't reward any intermediate actions. Rewards can also be periodic, at each time step or at the end of an episode. They can have non-linearities, for example, when there are diminishing marginal returns to one sort of element or in a vector of valuable goods, for example. The Cobb-Douglas function is a utility function that is sometimes used. And you have constant trade-offs between any two elements of outputs that you value, and each element is diminishing in returns. So for example, you might value ever more attention on your in your social network feed, but other things are important too, like decency and helpfulness, etc. And you must, of course, turn every wish into a quantifiable metric that makes sense. The business metrics that you care about go into this utility function. After all that, there are trade-offs that you might have to make. The utility or reward or cost function tells you how to make them, as it projects any vector of concerns and priorities into a one-dimensional scale that represents your preferences. You could say that this same object has too many names, but this has to do with the historical development of these ideas. So different names that you see, the different disciplines from which the ideas here have been influenced. Whatever you call it, choose to call it, utility, cost, or reward function, you must get this one right, so that the algorithm is learning how to behave optimally given your preferences. To accurately represent what you want is the hard part. This can be cleverly achieved with some methods from economics that are out of scope here. Anyway, the next thing you have to worry about is the agent. The agent consists of two parts, the policy and the learning algorithm. For small action state spaces, we can use something called Q function, which is simple, but most often is not relevant. What is special about neural networks here is that it is a neural network is a universal function approximator. This means that it can take the whole state space and approximate the most optimal response at every time, given the utility function over the outputs of the system. I know this is quite technical. No question about that. But from a highly complex state space, that has all sorts of nonlinear relationships that would be hard to formulate in an analytical expression. Well, these neural networks are really great. This is all assuming a policy gradient approach, which is compatible with a stochastic policy. A stochastic policy is great in games to keep the opponent from learning your policy, and is great for exploring the state action space as well, because you're taking actions, in a probabilistic way. You're not taking always the same actions, right? So you're harder to predict, and you're also exploring the space of possible actions that way. Algorithms which keep a balance between the exploring new actions and ever-changing in an ever-changing environment, and exploiting what they already know that works, they do better in the long term. It updates its policy roughly by executing its current stochastic policy, then collecting the rewards, and then if the rewards of the action turn out to be good, it increases the probability of taking this same action ever so slightly. And else, if it was not good, then it decreases that same probability ever so slightly. And so it goes on. A child might try out a new trick on a bike and then it falls, because some slight motor action that it took was not as it should have been. And then the child learns to adjust its behavior and falls less often.
Okay, that's great. So can there be multi-agent reinforcement learning as well? And are there real-life applications for multi-agent reinforcement learning?
Yes, absolutely. And I think that those are some of the most fascinating systems. Actually, it's a bit related to my TED Talk, because we're entering here in the field of collective intelligence. In broad strokes, we can distinguish between adversarial and cooperative multi-agent systems. For learning to play games against ever more powerful opponents, for example, adversarial multi-agent reinforcement learning has proved incredibly effective. And this sort of learning is clearly also relevant to cybersecurity, for example. But less obviously, it is also relevant for imitating works of art and for generating imagined photographs. It's really interesting. But then my favorite one is cooperative agents. And they, on the other hand, if they're installed on construction drones, for example, could work together to construct new office buildings entirely autonomously. Multi-robot factories will cooperatively optimize entire production processes. Autonomous vehicles can work together to optimize traffic flow. Most interestingly, I think, cooperative multi-agent systems might foster cooperation in human collectives to better solve complex problems. DeepMind has a program where they work on this problem, and so does the Alan Turing Institute. Think about global challenges that are in part challenges for more cooperative competence. These include pandemic preparedness, preservation of biodiversity, economic development, reduction of ongoing risks from war, and so on. All of these could be helped by multi-agent cooperative agents. And among cooperative agent systems, the agents may be communicating, or they might not be communicating. These are two types of systems. A further distinction can be made is in team learning and concurrent learning. I think the more interesting one is concurrent learning, because each agent learns on its own to modify its behavior as before. And this is the more truly multi-agent system, because team learning is really only has one learner that centrally learns how every agent should behave. However, the team learning approach can get around some of the harder parts of making the concurrent learning systems work, because there are some issues with them. But the games there's some really strange behavior that sometimes arises. The games that we have explored so far, chess and Go, are all two-player games where players are playing against each other with no possibility of cooperation. With a larger number of agents, things get both completely intractable mathematically if you want to solve for some equilibrium, for example, as economists often want to do. But they also get more interesting in terms of the possibilities that such a system might have. This opens up the possibility of cooperation between agents, such as you would have in robotic soccer, for example. In practice, these systems exhibit unexpected dynamics between cooperating agent and non-stationary environments, and they have other complex issues that prevent them from being rolled out en masse as of yet. but they hold enormous promise.
So in terms of data collection, is it really required in reinforcement learning?
Data collection stuff? No. They're pretty much not required. Data is generated most often in a simulated environment where agents are trained, and sometimes for online learning from the real environment and the actions that the agents take. So in those cases, there's actually no need to collect static data as before in most other algorithms.
Okay, and how would you distinguish between model-based and model-free algorithms?
That's really interesting, right? So model-based algorithms can incorporate prior models into their learning. So like you and I, we can learn about exactly how physics work, and maybe that will give us an advantage when we start playing pool, or when we start doing some physical activity, if we understand how it works, right? So they don't start from scratch, but they can already start with a model of how at least part of the action state space works. Not necessarily the whole action state space, but some part of it. And then they can keep learning from there. So model-free algorithms start from scratch. They don't learn anything. They learn everything from scratch, right? So they have to learn how everything works, including gravity and so on. Whereas a model-based algorithm doesn't. That has already a model.
Okay, and in terms of their applications, in different real life scenarios?
Yeah, so the distinction that I'm aware of is between policy function-based and value-based function or actor-critic. Do you mean those?
Yeah, so maybe we can discuss value-based, policy-based, or model-based methods and how are they different.
So I discussed how a policy gradient approach might work, right? This is what I talked about earlier. And the value function approach is quite different, really. For people who have come across the optimal control literature, the agent is trying to optimize a type of Bellman equation. This is very technical. You might not know this because you might not have come across this, right? But at each time step, the agent takes some action or some set of actions, and then it is rewarded, and then it calculates the value of having taken this action. It criticizes it in a way, if you will. And this is a bit difficult to explain well if you haven't encountered it, without getting into equations. But it is otherwise in practice also limited to a rather small action and state space, and thus it's not as important. An interesting method, though, is a hybrid version. It's the merging of policy gradient and value function-based approaches to arrive at an actor-critic algorithm. This requires two neural networks, known as the actor and the critic. The actor optimizes the policy gradient as we discussed before with the policy gradient optimization. And then the critic reports back what value it thinks an action produced. It itself is rewarded by how far it was off from the actual value that was realized. And then the actor then gets the feedback from the critic to adjust the probabilities of taking a similar action in the future. And with these two networks, you can take the advantage of both of the benefits of both the policy gradient and the value function approach, if that makes sense.
So, what are discrete and continuous action spaces?
So that's a good question. A discrete action space is one where at every turn, at every contingency, you can express, you can take an action from a list. You can think of it like a multiple choice. You have multiple choice lists. You can choose one of a number of actions, discrete actions. So, for example, you could start driving. When you start before you start driving, you might choose a destination. Right, that is a discrete choice. I'm going to Italy. I'm going to France. Maybe I'm going to Hong Kong. Whatever it is, right? That there's a discrete number of places you can go to. Whereas a continuous action space is when your choice is about a quantity or an amount. If you drive, for example, the amount of pressure that you exert on the gas pedal at any moment, that is a continuous choice. Or the temperature that you set on a thermostat is also a continuous choice, if that makes sense.
Okay, and what are transforms? What role do they play in reinforcement learning?
Oh, this is a great question. Transformers are neural networks. In essence, that are equipped with a mechanism of self-attention. differentially weighing the significance of each part of an input data with respect to other parts of the same input data. It's a bit tricky to think about this. It is often used in the fields of natural language processing and computer vision. It's better, if you have good examples, this would illustrate it well. There are, if you, for example, translate something from English to French, there are often cases where, can't think of one right now, where a noun phrase is sort of reversed, basically where if you translated it word for word, it would sound wrong in English because it would have the wrong order, whereas in French it would sound wrong if you translate it directly from English to French. And because you need this sort of reversal of concepts, for example, this is a very famous example of how they use this, how they demonstrate this attention mechanism. It sort of knows to pay attention to other nouns to form this full noun, and it also knows that in French, the attention would be, it would tell it to basically reverse it. So it's a little bit tricky to explain this, but it's very important, this thing called the attention mechanism. It's often used in fields of natural language processing and vision, for this reason. However, it is useful for any task that could be framed as a sequence prediction task. This is important here for reinforcement learning. An action, namely, can often just be interpreted as another link in a chain of events. And chains of events with different actions within them can be even evaluated and then compared. We might call this conditional sequence modeling. Conditional because the sequences are conditional on the actions taken by the agent. The significance of these newer models relative to earlier sequence modeling architectures, namely recurrent neural networks, including the very famous long-term, short-term memory network, LSTM, is that they allow now for parallelization where the other approaches did not. So in LSTM, for example, you would have to go, your learning mechanism would have to consider every link in a chain, in a sequence, after it considered the other ones before, right? So it has to visit every node in order. Whereas in this new approach, in this in the transformer approach, you have this embedding for each link in a sequence, which includes a positional element, and that allows it to process the entire sequence in parallel. This means also that we can handle very large action state spaces or many correlated sequences in order to predict what would be the best action in one of the sequences at one point in time. A recent paper that introduced such a model, which they called decision transformer, has, according to authors, beaten or matched state-of-the-art reinforcement learning performances on a bunch of tasks.
Okay, that's great. And now, how about offline reinforcement learning? How does that work?
Oh, yeah, okay. Offline reinforcement learning is where you do need to, collect a data set again. So this is used to learn optimal policy from a fixed data set of prior action states and rewards. The policy that was used to generate the actions that are in the data may or may not actually be known. The fact that the data is fixed can sometimes significantly mitigate potential risks and costs by not requiring any additional exploration. However, of course, the lack of ability to explore has its own costs, and if an environment can be sufficiently accurately and cheaply simulated, then it is most often better to learn dynamically and to allow for exploration in particular. In the case of the fixed data set, it might be sufficient if all possible actions are taken in all possible circumstances at least a few times. This might not be the case if some important circumstances arise only very rarely, for example, and there you might have a problem.
Okay, so in your expert opinion, where do you see the future of reinforcement learning? Where is it heading?
Yeah, well, certainly there are a number of things I find interesting to see if they come to full fruition. In particular, I care a great deal about cooperative multi-agent systems, as you might have gleaned from my enthusiasm around your question about that topic. I hope that we bring the most powerful systems to bear on our most difficult and important problems such as climate change, mitigation, adaptation to climate change, healthcare, very important topic, rewilding and rejuvenating of our post-industrial wastelands, and perhaps most of all, to foster more cooperation and more goodwill between human beings. Can these reinforcement algorithms help us where we seem to be weak and where we often fail? Can these algorithms throw us into deeper problems than the ones that we are trying to solve by means of misspecification of our problems or the reward functions? I think so. These are questions that I tend to think about.
Yeah. So in terms of anybody who's actually working with reinforcement learning, maybe a startup, what challenges do you believe that they will face when they start working with it?
Well, deep neural networks, which is what in practice most of these systems are based on, are black boxes. And if something doesn't work as it was hoped, then it isn't clear how to fix it. That's one problem. It's similar to a human being making decisions. It's also a black box, actually. It's interesting that people ascribe this black box nature only to AI, when in truth, you ask someone, why did you take this decision? They will usually post-rationalize it with something and give you some explanation. But it's not at all clear that their explanation is the real, really explains their actions, right? So just want to make sure that this, understood. Now, the only option then is to retrain once you have this problem, you notice a problem in the system and you want to fix it, you have to retrain the whole agent, and then you have to take the new, taking the new conditions or considerations that came up into account. Another related issue is that if the agent behaves well in some settings or states of the system, there is no guarantee that it will behave well in other states and contingencies. There might be too many possible states to test the system in a satisfying number of them to feel safe about its behavior. Some of these things can be partially or mostly overcome by training in many different simulated environments, for example. There are other ways to make the policy more robust to unknown states as well. It is noteworthy, though, from a business perspective, that there are no self-driving cars currently on most city roads, although there has been a lot of training and there are a remarkably low number of accidents, considering the driving hours that some of those algorithms have under their belt. Why is that? If a human is an accident, right, we brush it off mostly off and say, oh, well, another accident. If one of those algorithms, however, has an accident, it is in the news. We have much lower intrinsic tolerance to machine failings than we have to human failings. Perhaps because we feel somehow more helpless when it is a machine that drives our car into another car or into a freeway divider, than if it is our relative or our friend who has a sudden lapse of ability or vision or whatever. We post-rationalize. That is, even so, the algorithm overall has a much better performance than the best human being alive. If the perceived possibility of crashing is not zero or really close to zero, then most people aren't inclined to even be driven by an algorithm. This might appear irrational, but it is nevertheless a practical concern that startups should think about.
With these algorithms, I think more and more humans are sort of losing when it comes to games like chess and Go and all of that. So where do you see this going? Because quite a few people are projecting very doomsday situation.
Well, I think that most tasks that can be specified by a human being, so I think that the task of specifying the problem will always rest with the human being. I cannot see that the task of actually specifying the problem will be given to an algorithm. But then once you specify it, and if you specify it correctly, because that is a very difficult one to do, then I think the machine will learn, will outperform us on most of those tasks. And I can, of course, I think personally, when it comes to art and music, I have no interest to listen to an algorithm play music for me. It doesn't really matter what this music is. It's not interesting to me because music and art to me come from humans. It's only interesting when because it's a human that I'm interested in. I'm interested in them expressing the feelings or something like that. I'm interested in a human thing when I listen to music. So I don't think in that area it's really too interesting. But in all of those areas, that I mentioned before, problem-solving areas, driving better, finding better, finding parking spots faster, and all of those things, it's this danger that we misspecify the problems, because if we do, in some areas, it can be disastrous. And there will be some things like that. I'm pretty sure there will be such things as that, and they already have been, and they will be in the news. They will be increasingly talked about, I hope. I think that's very important. And then ultimately, there will be also very, very successful ones. And so I think it will be going on like this for a long time. We will try to find out, what does it really mean to build ethical algorithms, right? I think we're even in a searching process to answer that question. And it's not an easy one. It's a complex one, because ethics are different between human beings. We have utilitarianism, we have libertarianism, and we have, for example, egalitarianism. These different schools of ethical thought, and they are actually conflictual with each other. So it's not clear how we're going to find a good path toward algorithms that we can trust, that most people trust, But we are working on it. We're learning it, and I think we are moving very fast. And for that reason, we will make a lot of mistakes, and there will be a lot of costs paid, human costs. But I do think that also in the same time, we're accelerating AI in healthcare, and we're serving people better than ever before. I think precision medicine and so on. And I think in those areas, we will have huge successes. And so it will be both successes and blunders, I would say. And that's how we will be, sort of plotting our path forward.
Mm-hmm. So is access to this technology democratic in nature?
So I think there's a very big move toward democratization of AI, and I think that's very great. In fact, Google is part of that. I think IBM is part of that. It's many people can now build AI systems, and it's relatively easy to do technically. It's still very hard to specify the problem correctly. I think maybe we will make mistakes much more, even faster when we have this democratization. But I think there's different levels of democratization. There's actually different types of democratization. There's a democratization where it's easy to build an AI system for anyone, and that's one way. And then there is a democratic AI. That is an AI that learns labels from what people prefer overall, right? So imagine you had an AI representative of a collective of humans. Right now we have humans representing us in Congress, for example, or in the Senate. And I'm talking about the US. It's the system that I'm most familiar with. That's just an example. It's similar houses of government are abound all over the world, and these people are representing us. But are they really representing us, right? So they might not. We could design AI that surely represents us, right? So that learns what we value, what different people in society value, and then it will be faced with this sort of trade-off, right? And that will be very difficult to design, because we don't want minorities to be overrun by the majority of people who vote or something like this. So it'll be very difficult to design this, but it will be basically along the lines of how we design the democratic systems today. But instead of humans representing us, it will be algorithms representing us, and there will be some advantages to that, because algorithms have no ulterior motives, right? If we can be clear what the algorithm's motives are based on, namely if it's entirely based on voting, then they can be extremely credible representatives of a group of people. And I think that's a different type of democratization. And I think that one is probably the more interesting one, actually.
Okay.
I mean, it's also interesting that everybody can build an AI system. That's also interesting. But, because of the difficulties of specifying the problem, it's not clear that the advantage is as great in that as it is in having an AI that represents humans in a democratic way.
So with the big players like Google and Facebook, where they have all the data with them, do they have an advantage in this field?
Yes, they have a huge advantage, right? So this is something not to forget about. So even if we can all build the same powerful AI algorithm, at home using Google technology or something like that, we will not have the data that Google has and that Facebook has. So yes, they have an unfair advantage, because this data should be ours. but it's theirs, right? They're not paying us for it. Somehow they own it because they created the system or something like that. And therefore they have a huge advantage because they can train their systems on massive amount of data that we provide. And they don't have to tell us anything about these algorithms, how they work. They don't have to give us pre-trained systems like that and that we can build on. No, that's, basically sometimes in transfer learning, there is this case where Google will, for example, train an algorithm and then they will make it publicly available. That I think is okay. That is good, right? So if you make the algorithm, so if you have the data and you're a monopoly you have a monopoly on the data, like Google does, and you train an algorithm, and then you make the trained algorithm available to people to actually modify it to allow for what is known as transfer learning. That is a really great approach to make that part more democratic, to make the data also useful for more people. But that is actually a pretty bad problem. This fact that a very few players have most of the data. Actually, Jaron Lanier speaks about this extremely intelligently. Recommend his videos on that.
Okay, so if anybody has to learn more or maybe start, which sources or books you would recommend?
I'm a huge fan of. I subscribe to a lot of things. I always read the Google technology blog, the Amazon technology blog, eBay, like all of the big ones. I often read them. I mean, it's like I'm basically, for me, it's my bread and butter. It's what I do. I live and breathe. Basically, I don't expect everyone to do that, but there's certainly books I could recommend. Here's one. Gives you a great idea. This is a classic. This is by Stuart J. Russell and Peter Norvig. It's called Artificial Intelligence: A Modern Approach. I would highly recommend this one. That's gives you a good overview of what AI is in general, not just the machine learning part, right? So all of the machine learning books that are out there are a lot of good ones. I would definitely, read that and work through examples and also build, the main thing, really, the absolute main thing is to actually build such systems yourself. And there are lots of, Google has these code labs, and this is what I do. I work through code labs, for example, that I see that interest me. For example, with respect to reinforcement learning, I work through a bunch of code labs and really familiarize myself with how it is done in practice, how these systems are really built, right? So I would recommend that for sure. That's top recommendation. And then in terms of ethics, there's this ethic component that I think is extremely important. There's another book that I could recommend here. It's called The Idea of Justice by Amartya Sen. And it's interesting because the ethical part of AI isn't all that different from the ethical considerations that you have to have when it comes to governing a normal, the traditional system, social choice, basically. Like the problems that show up in democratic systems, why certain things don't work as they should, or for example, this problem called the Arrow's impossibility theorem is a famous theorem in economics and welfare economics, I think, and that basically shows that it is not possible to have four axioms that you feel like they have to be part of this system, right? But they can't all simultaneously hold. And this is a tragic thing. But these things are important to be aware of in terms of ethics. And I think that, AI has a few extra considerations when it comes to ethics. I mean, the bias and the privacy concern. I do think that the unexplainability issue is actually a little bit overblown in the sense that I don't think you can explain human behavior either. And so this is, the only alternative that we have over an AI decision maker is a human decision maker. And you cannot explain how the human decision maker works. So I wouldn't disqualify the AI based on its unexplainability, because the alternative is equally unexplainable. But definitely the biases and the privacy concerns. There's a movie called Coded Biases I would watch, That's really interesting, and it shows how things can go badly wrong. So I definitely would be concerned about the ethical aspect a lot, and there are great books about this as well. And there are constantly new books about it. And the thing is that we are really working on it. It's a work in progress to really figure out how to build systems that are on balance. Prefer that there are systems that we really would want to have, right? That benefit humans, human freedoms.
Okay. So, Johannes, thanks a lot. Truly appreciate all of your time and energy. And we are very much looking to having you back